Hey everyone, welcome back to Truverack Labs. Today we're diving into something super cool, how machines actually understand those quick TikTok videos and short clips you scroll through every day. It all starts with preprocessing, breaking down the audio, the text overlays, and of course the video itself. But here's the thing, video is really just a sequence of images playing one after another, so we're gonna focus on the fundamental question: how does a machine look at a single image and figure out what objects and scenes are actually in there? So first off, what even is an image? At its core, an image is basically a huge grid of numbers, like a giant matrix. Each spot in that grid is a pixel, and the number assigned to it tells you the color. 0 might be black, 255 might be white, or you get mixtures of red, green, and blue values for full color images. So that selfie on your phone, it's literally thousands of rows and columns of these numbers arranged together. You can think of the whole thing as a big array of tiny vectors, or what we call image embeddings when we get into the more advanced stuff. Now back in the day, before deep learning took over everything, we used what are called classical methods to pull useful information out of these pixels. One of the big ones was histogram of oriented gradients, or HOG. This technique looks for edges in the image and figures out which direction they're pointing. It's really great for spotting shapes like people or cars. Then you've got local binary patterns, LBP, which examines the texture around each pixel. Is this area smooth like skin or rough like fabric? And there's scale invariant feature transform, SIFT, which finds key points in an image that stay consistent even if you zoom in, rotate the image, or change the lighting conditions. Once you extract these features, you can localize the object, like drawing a bounding box around a dog, and then classify it, saying, okay, that's definitely a dog. This whole approach is what we call theory-based feature engineering. It means humans are using math, physics, and knowledge about how human vision works to handcraft these features. We're not letting the computer guess randomly. We're telling it exactly what to look for based on solid principles and domain expertise. Here's how this works step by step when you're doing video analysis. First, preprocessing. You break the video into individual frames, clean up any noise in the images, maybe subtract the background to focus only on the moving objects. All of this is grounded in image processing theory. Second, feature extraction. For spatial features, meaning what's happening in a single frame, you grab edges, textures, and shapes. For temporal features, you track how things move over time, like following the path of an object across frames. Spatiotemporal features combine both dimensions, treating a chunk of video almost like a 3D block where time is the third dimension. Third step, transform and select. You normalize all those numbers, reduce the dimensions using something like principal component analysis from linear algebra, and pick out only the most useful features for your specific task. Finally, you feed all these carefully crafted features into classic machine learning models like support vector machines or random forests. These models then classify what's happening, like is this normal behavior in a surveillance video, or is something unusual going on? But these days, deep learning has become way more popular, and for good reason. It's what we call data-driven or automated feature engineering. Instead of humans designing every feature by hand, the model actually learns the features straight from the raw data. It can handle all the messy real-world stuff that handcrafted features struggle with, things like bad lighting conditions, weird camera angles, objects blocking the view, or unpredictable motion patterns. The variability in real video data is just too much for manual feature design to keep up with. The process for data-driven approaches is actually simpler in some ways. You prep the data minimally, just resize the frames to a standard size, normalize the pixel values, and convert everything into tensors or sequences that the model can process. Then feature learning happens automatically through layers of the neural network. The lower layers pick up really basic stuff like edges or simple colors. The higher layers build up progressively to recognize complex things like human faces or specific actions. The whole thing optimizes through backpropagation, constantly tweaking the internal weights to reduce errors on whatever task you're training it for. You refine the model with techniques like dropout to avoid overfitting, where the model memorizes training data instead of learning general patterns, or you use autoencoders to compress information. The key difference is there's no need to handpick which features matter, and it all integrates end-to-end, meaning the learned features flow directly into the final prediction without separate processing steps. Let me give you some concrete examples of how this works in video analysis. For spatial features, we use convolutional neural networks, CNNs. These networks slide filters over the image and learn patterns automatically through training, way better and more flexible than those predefined HOG kernels we talked about earlier. CNNs are used in object detection systems like YOLO for tracking things in real time, often with powerful backbones like ResNet or EfficientNet handling the heavy lifting. For temporal features capturing what happens over time, we use recurrent neural networks or their more advanced cousins, LSTMs, long short-term memory networks. These process video frame by frame to catch sequences and motion patterns. They learn dependencies over time, like understanding that certain movements follow each other. They can struggle with really long sequences because of something called vanishing gradients, but they're perfect for action recognition tasks. Is someone running, dancing, or waving? For spatiotemporal features, combining space and time together, we use 3D CNNs like C3D or I3D. These apply convolutions in 3 dimensions to grab both motion and appearance information simultaneously. They're really good for short clips in anomaly detection, spotting unusual events in surveillance footage, but they eat up a lot of memory when you're dealing with long videos. There are also unsupervised approaches like autoencoders or variational autoencoders. These squash the video data into a small latent space representation and then try to rebuild it. By learning what normal video looks like, they can spot anomalies. If the reconstruction error is high, meaning the model can't rebuild the video well, that's a sign something unusual is happening. No labeled data needed for training. Then you've got the newer transformer-based models like TimeSformer or ViViT. These use attention mechanisms to link important parts across different frames without needing a strict sequential order. They're fantastic for handling long-range dependencies in videos, perfect for tasks like video summarization, where you need to understand the big picture. The downside is they need massive amounts of pre-training data to work well. Even generative models like GANs, generative adversarial networks, play a role. You've got 2 networks competing, a generator that tries to make fake video content and a discriminator that tries to spot it. Both learn really deep features through this adversarial process. This is super useful for data augmentation, creating more training examples, or for catching deepfakes by understanding what real video distributions look like. Whether you're using the old-school methods or the new deep learning approaches, both are trying to do the same fundamental thing, turn raw visual or audio data into vector embeddings, these compact numerical summaries that capture the important information. Here's how it all flows together in a real pipeline. You start with video frames feeding into a visual language model, or audio tracks going into an audio language model. Both get processed and converted into embeddings. Then a large language model takes those embeddings, combines them with any text instructions or context, and produces the final human-readable output. Something like, this clip shows a kid doing a prank with a trending sound and a funny text overlay. At Truverack, for our video analysis pipeline, we use small VLM2 to embed and understand images from video frames. We use OpenAI Whisper base to process and transcribe the audio. Then we use Gemma 2 to pull everything together and summarize it all into readable, understandable text that describes what's actually happening in these short videos. So that's the gist of how machines see and understand images and videos. The old way, smart humans design features based on theory and domain knowledge. The new way, you feed massive amounts of data to neural network models and let them discover the patterns themselves. We mix and match these approaches depending on the specific job and requirements, but for dealing with the scale and variety of TikTok content, the data-driven deep learning approach definitely wins out. There's a paper linked in the description with way more technical details if you want to dive deeper. It's from RZiv, number 2501.14828. So what video trends should we analyze next? What are you curious about? Drop your suggestions in the comments and let me know. Thanks for watching, and I'll catch you in the next one.